Let's talk about the most important feature of one of the most important experiments that we saw was Rutherford's gold foil experiment. Everybody get to that section? So let's take a look at this simulation. Let's see. Rutherford scattering. So what happened here is we had this grad student. His name was Rutherford, and he was actually working with radioactivity. He wasn't really looking into the structure of the atom necessarily, like particularly, but at the time, J.J. Thomson had said that essentially atoms were homogeneous mixtures of protons, neutrons, and electrons, right? So this table is relatively solid and homogeneous. Materials seem to be kind of homogeneous, right? Evenly mixed up. So his theory, J.J. Thomson, was, this is the guy who discovered the electron. He said, essentially, it seems like things are kind of evenly mixed here. Neutrons, protons, and electrons kind of evenly mixed throughout this material. That was his theory. So what this gentleman Rutherford did, and let's connect this idea to what we did last time, which was we talked about nuclear notation. What Rutherford did is he took this material, radium, and the symbol for that is Ra, and he took radium-226. So let's dwell on this for a moment. Radium-226, take a look at the periodic table I handed you the other day, and tell me what number should I write right here, bottom left-hand corner. What should I write right there if I'm working with radium-226? This is a throwback to yesterday, right? We talked about nuclear notation. Ra is a symbol for radium. 226 is called, this number is called the mass number. It represents the total number of protons and neutrons in the nucleus. This number right here, the one that I'm asking you for, this is called the atomic number, and its symbol is Z. This represents just the number of protons. The number of protons. This mass number, its symbol is A. All right, so the symbol for the mass number is A. The symbol for the atomic number is Z. Okay? With me so far? So look at your periodic table. What atomic number should I assign radium? It's over here. Bottom left on the periodic table. What do you got, Tom? Looks like 88. Top left, the atomic number on your periodic table, the one I handed you, is top left. It says 88. So I'm going to write 88 in here. That's the number of protons. That's the number of protons. I've got 226 total neutrons and protons, and I've got just 88 protons. With me? Okay. So let's say I've got this radium. I've got this radium stuff, and it's got 226 total nucleons, protons and neutrons in the nucleus, and it's got 88 protons, and it undergoes what's called alpha decay. Okay, so this is called alpha decay. And what that means is that it gives off a helium. Look on your periodic table, top right. Tell me, what two numbers should I write here? What should I write? Top left and bottom left. What should I write for helium? What do you think? Okay, if I write top left 2 here, that's actually called a diproton. It's very unstable. Watch this, okay? If I go to PhET, if I go to the build an atom module, if I add just 2 protons, look at the stability. It's not stable. It's not stable. I have to add 2 neutrons, this is the most stable form of helium. So what should I write? What are the two numbers I should write, Tom? There you go. So I should write, instead of a 2, I should write a 4 up top left. Now, how could I tell that just from my periodic table? How could I tell that a 4 should be written here? It's actually kind of easy. The reason that the weight, see the weight for helium, it says 4.003. The reason it's not quite 4 is because of the presence of isotopes. What's an isotope? We defined it yesterday. Same element, different number of neutrons. If I had a different number of protons, it would change the element. So same element, so same number of protons, different number of neutrons. How do I tell that 4 is the most stable form of helium? Easy. Its weight is right next to 4. That means that the most abundant isotope is 4. Because when I measure it and I almost get 4, that means most of that stuff is helium-4. That's how I know. So you can go by the weight. That will tell you more or less what is the most stable form of that element. Does that make sense? Is that cool? So I'm going to go with 4 and 2. That's helium. That's the most stable form of helium. If that's the case, if I had radium and I let go of helium, what would I make? I have to conserve matter. What would I make? What number should go here and here if I'm going to conserve matter? Look at the left side of the equation. I've got to have these numbers add up to these ones. I have to conserve matter, so that means that these numbers have to add up to these numbers. It has to be conserved. So what should I have right here? What should I have in this position? I get 226 gas. I gave off 4 of them. So what do I got? 222. 222. What about this one? What about the number of protons in this new thing over here? Yep. Should be 86. Good. So now we've conserved matter, which is good. All right, let me actually just rewrite that briefly so you can actually see it. That's not an eraser. I thought that was an eraser. So 222, and 86. Now, look at your periodic table. Find me number 86. What is it? Rn, radon. This is the stuff in your basement. In New Hampshire, this is the stuff that's in your basement, usually needs to be vented from your basement. It causes stomach cancer. So it is itself, this is not very stable. In and of itself, this is not very stable. Say again? Asbestos causes a lung ailment because it's like tiny little fibers and it sticks into your lungs. So this is alpha decay. Everybody kind of follow along with this. I just wanted to show you this so you could use those skills of nuclear notation just to remind you about what we did yesterday. All right, so top number is the total number of nucleons, protons, and neutrons. Bottom number is called the atomic number. It's the number of protons. If you change that, you change the element, right? You change the element. If you change the number of neutrons, you just made an isotope. Nice. Okay, so let's look at FET, and let's actually go back to Rutherford. There he is. Okay. So again, Rutherford was a grad student studying radioactive decay, and what he did was he took this alpha decay and he concentrated the alpha particles on a gold foil, so on a piece of metal. What do you think? Hypothesize for a moment about what you think would happen if you shot these particles at a piece of metal. What do you think would happen? Cynthia, what do you think? If I hit a piece of metal with some particles, what would you expect to happen? For it to come back, you'd expect it to bounce right back. So Cynthia is saying all of these should actually just come right back at us because it's solid. At the time, remember J.J. Thomson was saying this stuff is homogeneous. There's no space in it. So I think to some degree that idea is very valid. Thinking this is homogeneous, it's all evenly mixed. If I shoot some stuff at it, all that stuff might just come back at me, bounce right back, right? Let's see what happens. If I turn on the alpha particles, those little purple dots are alpha particles. They're going through the gold foil. This is a blown up section of this gold foil. You can see it at the atomic scale. So what is this scale right here? What do we say? It's like this is about an angstrom, right? 1 times 10 to the minus 10 meters. 1 times 10 to the minus 10 meters, rather, not 10. So look at what's happening. The vast majority of these alpha particles are landing on the back detector. They're actually going right through. So only every once in a while does something strike this nuclei in the center of the gold and get deflected considerably. See, this one just came all the way back, and then it came this way. Right? So a lot of deflection happening if and only if it strikes the nuclei. And you'll see some of them, watch very carefully, you'll see it doesn't really touch the nucleus. It actually gets close and gets repelled. What force is making that happen?
Like forces or whatever.
Yes, they're like charges, so the electromagnetic force, right?
Yeah, because when you have so say you'd have either 2 positives or 2 negatives.
2 positives, 2 negatives, they'll repel. So that repulsion is happening because of like charges, but in addition, it's massive, right? So if 2 massive things hit, you get an equal opposite reaction. If it's a direct strike, you'll notice they deflect really, really badly, right? They might almost come right back. So when he built this detector, he built it all the way around this thing, and he saw that a lot of the particles, or some of the particles, come all the way back. They'd get deflected at these really extreme angles. Those are the ones that directly hit a nucleus. So what this did is it showed us that this is not a homogeneous mixture, this solid. It's not a homogeneous mixture of protons, neutrons, and electrons. In fact, it's all of the charge and mass is concentrated in this tiny little space, and then the rest of it is filled with electrons that occupy very specific energies. So this idea of them occupying very specific energies, that is our next piece of information we have to digest, is that it turns out that not only are protons and neutrons concentrated in a very, very tiny space, and the rest of the space is taken up by electrons, but those electrons orbit at a specific energy level. So if you shine light, I know this is hard to see now, but I turned the light on. If you shine light on a hydrogen atom, it gives you very specific colors back. It doesn't give you a broad range of colors. It gives you just exactly these colors. And what that tells us is that when light hits a nucleus, if it strikes an electron, that electron might move up to the next orbit and fall back down, re-emit light, and that light will be of a very specific energy, corresponding to the energy of that orbit. So that's a lot. We're going to dwell on this concept for the rest of the unit. This is what your competency is based on. All right? And you have to understand light to understand this. That's why we started out with light. But for right now, I just want to show you a particular skill related to understanding the structure of an atom. We'll call it the Bohr model. Okay? And here's what the Bohr model says. If I were going to diagram hydrogen, in the center of the diagram, I'm going to put the number of protons and neutrons. So I'm going to say there's 1 proton. I'm going to put that in the center. And there's no neutrons in the most stable form of hydrogen. It's called protium. There's no neutrons. So I'm just going to leave it just like that. Now, how many electrons would there be if this thing was neutral?
1.
There'd just be 1. So I'm going to make an orbit, and I'm going to fill it with 1 electron. This orbit I'm going to call n equals 1. That's the principal quantum number. That's the principal quantum number. It corresponds to a very specific energy. This has a very specific energy that is related to its speed and its position. So, is there attraction between this electron and this proton? Yes, there's electromagnetic force acting on this system, yeah? There's electromagnetic force acting on this system. There's a positive charge and a negative charge. They're being attracted. And that's why the electron is, in part, moving as fast as it is, right? That's why it's moving as fast as it is. So this original model is almost like a planetary model. You're seeing this electron as an orb rotating around another orb, right? And it has a certain speed, and that's based upon its distance. Remember Coulomb's law from yesterday? It's based on its distance and its charge. So, suffice it to say that this first orbit corresponds to a specific energy. So that's hydrogen. Let's do this. Let's just list the principal quantum numbers for a second. I'll tell you how many electrons go in them. You ready? This first principal quantum number, it can hold 2 electrons. The second one can hold 8. The third one, that doesn't look like an equal sign to me. The third one can hold 18. And the fourth one can hold, if you're seeing a pattern, 32. Okay? So that's how many electrons can be held by each of those principal quantum numbers. And it's going to be the same for 5, for 6, and for 7. All of those hold 32. Oops. 32. Okay, so each one of those holds 32. So let's now do helium. Let's do the diagram for helium. If I was trying to diagram helium, what would I do? What would I put in the center? What would I put in the center, guys? 2p, right? And how many neutrons? 2. So 2 neutrons. I'll put that in the center. And then there's going to be 1 orbit. This is the n equals 1 orbit. And I'm going to put 2 electrons in it because in order to be neutral, helium has to have 2 electrons. Does that make any sense? Okay. Now, with your group, I want you to try to draw